Okay. So, as I mentioned a little bit ago, I work in radiation safety. So one of the things we want to do is we want to figure out sometimes how long can somebody stay in an area and still be safe when there might be radioactive material in that area. And the example we have here today is a room that's 6 meters across and 6 meters deep. There's a door here, and here's a person standing in the door who may need to do work. Okay? Through the middle of the room, there is a water line, a cooling water line, and that cooling water contains radioactive material. And the radioactive material that we're talking about in this example is iodine-131. And iodine-131 is a radioactive material that's very commonly used for making radioactive drugs, especially drugs that are used for diagnosing and treating thyroid cancer. So, in our example, we have a cooling line, and we know the concentration of radioactive material in the line, and the concentration is 10 curies per meter. Now, the curie is the traditional unit for expressing the amount of activity or the amount of radioactive material present. So, in every meter of this line, there is 10 curies of radioactive material. And each of those curies of radioactive material spread out through this line are emitting radiation, which is going to be potentially exposing an individual standing at the door. And we know how much radiation iodine-131 creates, and we express that as a gamma constant. And the gamma constant for iodine-131 is 0.22 rem meter squared divided by curie hour. And that's a little bit of a strange unit, but that's how the radiation, that's essentially an expression of how much radiation you would get from a curie of iodine-131 if you were standing 1 meter away from it. Now, the way we use it in this particular problem is that we use this formula here, which is x dot, which is the exposure rate, is equal to 2 times the gamma constant times the concentration of radioactive material in the line divided by h, which is the distance from the line, the closest point of approach from the line to the person, and that term there is multiplied by the inverse tangent of the ratio of L2, which is the measure, the length, this length here, and h, which is this distance here. So you plug those values into the equation. You plug the gamma constant into here. You plug the concentration in the line here. You plug the 2 dimensions into here, and you have to clean up all these units, cancel the units to make sure that you're going to get a usable result. So you go through here, meters cancel here and here, but this is a meter squared function, so another meters cancels. Curies here cancel, and what you're left with is R per hour, rem per hour, which is a measurement of radiation dose per hour, which is the result we're going through for. So after cleaning up all the units, we get a fairly easy looking equation that we can solve. And we multiply the terms through in the numerator, divide by 3 in the denominator, and we then multiply it, or rather right now we multiply this term, this simplified term, times the inverse tangent of 3 over 3, which is the inverse tangent of 1. And the value we get is 1.46. And this can come out in units of gradients or rads or degrees. But for the sake of computational ease, just to make it easy on ourselves, we express it in terms of pi. And the inverse tangent of 1 is pi over 4. Pi over 4 is equal to 0.785 times 1.46. And the answer is that the exposure rate for a person standing in the door at this distance away from this line containing 10 curies per meter of iodine 131 is 1.15 R per hour. Now, what does that mean? Well, the law says, in other words, what does that, how can we use that answer? The law says that no one is allowed to receive more than 5 R in a year. And every company that I've ever seen in the United States sets an administrative limit that's usually 1/10 of that limit to make sure that everybody stays well and safe below this limit here. So everybody is operating with an administrative limit of 0.5 R per year. Okay, so if you are allowed to receive 0.5 R per year and you have a dose rate of 1.15 R per hour, you can tell very quickly that you can spend less than an hour here. In fact, you can only spend 26 minutes here before you reach your maximum stay time, before you get as much radiation as you're allowed to receive in a whole year. So using this kind of information, a health physicist and engineers can get together and they come up with tools and ideas to either reduce the amount of radiation or reduce the amount of time needed to stay in this area, or to increase the shielding between where the person is working and the pipe to make sure that they reduce the amount of radiation to anybody who is actually standing here and working. So this is an application of how we use trigonometry in radiation protection.